Now, for this session, double check my time, 2 more minutes. But I always like to use this time to introduce my speaker. Well, not my speaker, your speaker, our speaker. You're not my property. It's Lukonde, I hope I got this right?
Yeah.
Lukonde, from South Africa.
Yes, originally from Zambia, but I live in South Africa.
We just chatted because you live in Johannesburg.
Yeah.
In Johannesburg, in Pretoria, where do you live?
Johannesburg.
Johannesburg, yeah. I was just there, and what I found fascinating, so I visited a lot of banks and financial institutions that you also consulted years ago. What I didn't know, South Africa is actually really good when it comes to cloud adoption, but most of their cloud workload actually doesn't run in South Africa, it runs in Europe or in North America. Which for me was interesting because latency is a big topic. That means for pretty much everything you do in South Africa, if you browse to a local website, you're basically making the way all the way from South Africa to Europe or to North America.
Back.
Yeah.
Right? Yeah, that's correct.
It's crazy.
Yeah, especially because there are a lot of hybrid systems. So that means the communication is Europe and then all the way back to South Africa.
And then a couple of other interesting facts from you. You are also a CNCF ambassador.
Right.
Yeah, that's why we took a selfie and had to send it in. And I can encourage everyone, if you want to also become like an ambassador for CNCF, just check out what it takes to apply and also what the good things are and what we get back and also what we contribute. Now, the last thing to your session is you, because I always ask people, why should people stay here, right? Yeah. You work for AWS, so I assume you want to sell a lot of compute.
No.
No?
Yes and no.
Okay. So you want to sell more, but on the other side, you also want to tell us how you can make your workloads more efficient. I think cost efficiency, performance is very important.
Yep, driving down your costs primarily in the Kubernetes networking domain, as well as doing that in conjunction with more optimal performance, low latency between some workloads.
Perfect. And instead of me standing here and asking you questions, I just give you the stage.
Yeah, sounds good.
And you tell us the rest.
Great.
All right, see you later.
Thanks a lot. I always like to confirm that the clicker is working as expected. This particular one has been misbehaving in the last few days. All right, hello everyone. Thanks a lot for coming to my session. Can you think of a better way to spend the middle of your afternoon in Vienna than taking in deep Kubernetes networking complexities with service mesh concepts thrown into the mix? There we go. For those of you that are silent or some that might be laughing, don't worry, I'll just interpret that as extreme enthusiasm. As you can see, the title for this session is Cheap Routes, Fast Paths, and Keeping Track. My name is Lukonde Mwila, and I'm a Senior Developer Advocate for Kubernetes at AWS. I'm also a CNCF Ambassador. For those of you that are interested in connecting with me, please feel free to do so after the session. You'll probably find me right here, but I'm also hanging out at the AWS booth with some of my colleagues, and you're more than welcome to connect with me online via LinkedIn. For those of you interested in watching cloud-native content, you can search for me on YouTube, just use my full name, or you can check out the AWS Container YouTube channel called Containers from the Couch. All right, now, I'm sure most of you would agree with me that managing network traffic in Kubernetes is relatively common. But also, depending on what you're trying to accomplish, it can become quite complex. And you'll notice that even as this session progresses. Let's consider some scenarios. If you want to manage the flow of network traffic for security purposes, such as which pods are allowed to talk to each other, you can implement network policies. And if you want to go a step further than that, such as enforcing that every pod first validates the identity of a peer before establishing communication, you can implement mutual authentication. Another example is if you want to manage the safe release of a new application version, you can split your traffic between 2 different versions of the same application. And depending on how things are progressing, if there are successful automated tests, you can increase the amount of traffic going to the new version. And if tests aren't passing, you can roll back to the previous one and redirect traffic to the previous version. Other increasingly desired patterns are those associated with cost optimization and low latency. And that's what I'm going to be focusing on in this particular session. Lots of teams are heavily invested in different techniques and strategies that they can implement to drive down costs in the Kubernetes networking domain. And the topic of Kubernetes networking and cost optimization is multifaceted. There's so many vectors and angles that you have to consider. And as much as I'm convinced that you're happy to be listening to Kubernetes networking in the middle of the afternoon, I'm not sure you'll appreciate it as much if we're here till 10 p.m. So I'm going to scope it down to load balancer to pod communication and inter-pod communication. Now, a lot of these costs are typically associated with, I went a step further than I should have. There we go. A lot of these costs are typically associated with cross-zone traffic movement. So that is traffic going from one particular availability zone to another, also known as inter-AZ traffic or egress cross-zone traffic. There are other angles, but this is the primary one. That's the cost side of things, but what about latency? Latency is very specific to the type of application that you're running. If you consider a large system, it may not necessarily be the requirement for every one of your microservices, but there may very well be some services that have a strong interdependency between them and require low latency in order for the application to function optimally. So, let's say you are a platform engineer, and some of you might be thinking, Luke, I really am a platform engineer. But let's assume everyone seated here is a platform engineer, and you're responsible for accomplishing these three requirements. But the two on either side of this image are the primary ones. So yes, you need to accomplish high availability for fault tolerance and resilience, but in addition to that, you need to drive down costs as well as cater to applications that have a strong interdependency in order to improve performance. What approaches would you take? And this is something that I've been noticing a lot with different teams, and I've assisted them during the course of this year. So I want us to consider three different approaches. And we'll spend a majority of the time on the third approach, which I'll also walk through in a demo later on. It's a recorded demo, but I'll jump to the relevant parts of that. But let's start off with the first approach. And this approach makes use of topology spread constraints, pod affinity rules, and the service internal traffic policy. Now, why would we make use of pod topology spread constraints? Just by show of hands, anyone making use of this in their Kubernetes environment, this particular native feature? Okay, so a couple of hands going up. So this is essentially what you'd be using to address the requirement of high availability. So if you want fault tolerance and resilience, and you want to spread your workload across different topology domains, whether those domains are nodes or hosts, then this particular feature comes in handy. The other approach would be to make use of pod anti-affinity. But the reason pod topology spread constraints is especially useful is because it allows you to essentially control the degree of spread so that you have multiple replicas spread across the different topology domains. So where does pod affinity come in? So pod affinity rules essentially allow you to create certain relationships between workloads, and then the scheduler attempts to respect the relationship between those workloads whenever it is scheduling pods to the node. And so because we're trying to cater to the requirement of low latency between certain microservices, this is essentially what would help us with that. We can co-locate pods on the same node because we want to reduce the amount of traffic, or rather, we want to reduce the distance that traffic travels between two particular pods. Now, some of you might actually be thinking, well, Luke, just because I'm co-locating pods on the same node doesn't necessarily mean traffic isn't going to traverse to a different node or an entirely separate availability zone. And you're 100% correct. So before we get to addressing that, I just have a quick code block over here that I want you to be able to see, that right at the bottom we have the topology key, and that's what we're using to configure the pod affinity so that the co-located pods get set up on the same node. The alternative would be to make use of availability zones. But in this case, because we're trying to minimize the distance that traffic travels, we would be setting it to the same host. But like I said, that doesn't control our traffic. So how do we actually restrict traffic? And this is where the Kubernetes Service Internal Traffic Policy can help. The Kubernetes Service Internal Traffic Policy essentially allows us to manage how traffic is distributed from the Kubernetes service to the different endpoints that it's responsible for proxying traffic to, those endpoints being the different pod replicas. Now, by default, the setting for the Service Internal Traffic Policy is set to a cluster-wide basis. So that means that the service is simply going to proxy the traffic to all of the replicas across the cluster. Now, that's not very useful for this particular use case. So what you can do is set that to local. And when you set it to local, that will essentially dictate the exclusive use of node local endpoints. And so if you take a look at this diagram over here, you'll notice that there's a dotted line between microservice A and microservice B, and they're represented by the blue and the purple pods. And so what's going to happen is whenever there is a request sent from microservice A to microservice B, in this case, we're assuming microservice B has the service internal traffic policy applied to it, and it is set to local. That means microservice A can only reach microservice B on the same node. So by implication, traffic never leaves the node, and by implication, traffic never leaves the availability zone. So we actually fulfill both requirements in terms of driving down costs as well as minimizing the latency of traffic. And I want to show you a code block over here. And so you see this particularly highlighted area is how you would actually configure or set that in your Kubernetes service. So you would set it to local. By default, it is set to cluster. Now, this is helpful to some degree. But I want us to consider things within the scope of load balancer to pod communication and inter-pod communication. This is helpful for inter-pod communication, but doesn't necessarily help us when it comes to driving down costs between a load balancer, an external-facing load balancer, that is, and the pods itself. So if you have a highly available load balancer that is responsible for proxying traffic into the environment, well, you're still going to incur high costs associated with the egress cross-zone traffic. So this helps us to some degree. Let's consider another approach. Once again, we're going to make use of pod topology spread constraints and pod affinity rules for the reasons that I already mentioned, but this time we're going to make use of topology-aware routing. By show of hands, anyone making use of topology-aware routing in their environment? Okay, I just see one hand going up. Oh, two, there we go, all right. So this feature is still in beta, but nonetheless, it's very useful. So topology-aware routing allows you to essentially increase the likelihood of traffic coming from a certain point of origin going to a destination in the same availability zone so that you can drive down costs associated with egress traffic across availability zones. And the endpoint slice controller is responsible for attaching what are known as hints to the different endpoint slices so that your proxying system is essentially informed on knowing where traffic should go based on where it's coming from. And the whole goal is to restrict it to a particular availability zone. So how does that help us in terms of the requirements that we're trying to accomplish? We already know pod topology spread constraints and pod affinity rules are helping us for the reasons that I already mentioned. Topology-aware routing is useful to drive down the costs associated with egress cross-zone traffic. But remember, we still have the requirement of low latency between certain microservices. And so we still have a constraint there. We're not necessarily helped in that regard. Now I want us to consider the third approach. Again, making use of the usual suspects, topology spread constraints with pod affinity rules, but this time I'm going to introduce Istio, specifically its destination rules, along with the service internal traffic policy. We're going to make use of these in conjunction. And some of you might be thinking, well, why can't we just use topology-aware routing with the service internal traffic policy? And that's a great question, and I wish we could do that. At this point in time, there is a constraint that prevents you from using those two particular features together. And so even when I was helping a particular team out with this, this is the route that we went because of that constraint. Hopefully that's something that will change in the near future. Right, so how exactly is Istio's destination rules going to help us out? So the destination rules allow us to apply policies to traffic after it has already been routed. So if you take a look at this diagram, you'll see that traffic first enters through the Istio ingress gateway. That's the entry point for the mesh. And then after that, traffic is then proxied to the virtual service. And the virtual service is responsible for routing of traffic. But then what happens to that traffic after it has been routed? Well, that's where the destination rule comes in. And the policy that we can apply to this is known as weighted locality distribution. So we can essentially distribute traffic to different zones based on where it is coming from, and we can apply weights to it. So if you can see in this diagram, I'm saying I want 60% of the traffic that is coming from the source to go to EU West 1A, and I want 40% of it to go to EU West 1B. And so you can essentially control where traffic is going to go depending on where it is coming from to minimize on cross-zone traffic. And I'm going to be demonstrating this a little bit later. Now, before jumping into making use of Istio, something that I do like to clarify a lot is it's a lot easier and better for a team in order to rather extend their use of Istio rather than adopt it just to make use of it for 5 or 10% of what it's worth. So I'm not advocating for the idea of adopting Istio just to make use of the destination rules, because that's going to cost you in another area. There's so much more to the service mesh. And so if you're already making use of it in your team, then I would encourage you to extend your use of it in this particular regard. But when you're combining Istio's destination rules with the Kubernetes service internal traffic policy, there are some really important considerations that you have to be able to work through, and I've highlighted them over here. The roles that your microservices are playing, the network traffic patterns in your system, as well as the deployed topology setup. When it comes to the roles that your microservices are playing, that's essentially going through the exercise of understanding what's the purpose of microservice A. Is it functioning as an API gateway, just receiving external traffic and then proxying that traffic to upstream services? And what is the purpose of microservice B? And this is a really important exercise and will lay the foundation for the other ones. As for the network traffic patterns, this is based on that foundation of the roles that the microservices are playing. You will be able to basically map or trace how traffic is expected to work through your system or flow through your system. And this can get complex pretty quickly, so I highly encourage making use of good tools like Cilium's Hubble. KubeShark is also another really good one, and ensuring that you have distributed tracing mechanisms in place so that you can generate the relevant traffic maps, but in addition to that, so that you can also be able to debug when necessary. Keyword there being when, because it will happen. And then the third one is the deployed topology setup. So understanding how you have deployed your cluster and the relationship that the pods should have with that particular topology setup. Is it necessary for microservice A to be on every single node or in every single availability zone? Should microservice B be co-located with microservice C on a node because of their interdependency or the relationship that they have? Those are the things that you want to be thinking about, and you'll see that come to play even as I work through the demo. And before transitioning into it, I want to cover some important components or aspects of the demo that will inform the walkthrough that I'll be giving a little bit later, so that no one gets lost in the weeds. All right, so I'm going to have 3 microservices in this system, and the first one is the GraphQL API. The GraphQL API is functioning as a data aggregator. It receives external requests that will come from the Istio Ingress Gateway, and then it will proxy traffic or send requests to either orders or products. So its only job is to perform as a data aggregator or some form of an API gateway. Next up is the Orders API. The Orders API receives both external and internal traffic. External traffic sourced from the Istio Ingress Gateway and internal traffic coming from the GraphQL API. And the Orders API can also send requests to the Products API. Now, in my particular demonstration, just so we're able to see the results of the network configurations and policies that I'll be putting in place, I have 2 different versions of Orders. And we'll be able to distinguish which version we're communicating with based on the results that we'll be getting back. But they're both fronted by the same Kubernetes service. And so what you'll see in the demo later on, before any policies are applied, there'll be somewhat of a 50-50 split in terms of how traffic is being proxied to the upstream replicas before policies are implemented. And so you're going to be able to distinguish which version of Orders is being communicated with. Orders 1 has a list that starts off with Bruce Wayne, and then Steve Rogers, and then Tony Stark, whereas Orders 2 has a list that starts off with James Lake Jr., Claire Nunes, and Tobias Domzalski. Third microservice is the Products API, but I'm getting ahead of myself. This is another important step just to understand. So for Orders 1, it only supports one endpoint, which is fetching all the existing orders, and that's the endpoint for it, whereas Orders 2 also supports an endpoint that has v1/orders/product. So basically, when you fetch an order, fetch the associated product as well. And third is the Products API. The Products API only serves internal requests. Similar to Orders, so that we know which version of products we are communicating with, there are 2 different versions of it, fronted by the same Kubernetes service. And once again, we'll be able to distinguish which one we're communicating with based on the data that we're getting back. So you'll see the two highlighted areas over there. One list of products starts off with a product called a Kubernetes t-shirt, whereas the other one starts off with an Envoy hoodie. Now let's consider the flow of network traffic. And so I'm also going to be making use of Kyali, and Kyali is essentially depending on Jaeger under the hood, as well as Prometheus. So this is important for the distributed tracing part, as well as the network traffic patterns that I spoke about earlier. And so this is just specifically to track the orders flow request. So as I mentioned, it is sourced from the Istio Ingress gateway, and then it goes to the orders Kubernetes service, and then you'll notice that there is a splitting or branching off taking place over there because traffic is being proxied between version 1 and version 2 of orders. Now, before we take a look at the GraphQL proxy, or rather the GraphQL network traffic flow, that is going to depend heavily on the type of query that you have for GraphQL. And so I've highlighted it over here, and so you can see for orders, I want to fetch all the orders, and for every order, I also want to get its ID, who the order is for, and the associated product. And so because the root part of the query is orders, that means that the GraphQL API will first communicate with orders. This will be easier to see with this traffic flow over here. So you'll see the purple line representing the initiation of the request. So first, GraphQL is going to communicate with the orders replicas. It will be communicating with both version 1 and version 2. And then after it resolves that data, that gets returned to the GraphQL API. Based on what it has received back from that, or its response, it will then communicate with the product's API. And next up is the deployed topology setup. So I've highlighted the relevant parts to make it easier to deduce this. Otherwise, you're just staring at a black terminal with a whole bunch of white text. But this is essentially the deployed topology setup that we're going to be looking at in the demonstration. And so we could start off by looking at the purple highlighted areas over there. Those are the different availability zones where each node has been deployed. AF South 1B, AF South 1A, and AF South 1B. And then if you look right at the top over there, you'll see that we have GraphQL, Orders 1, and Products 2 all on the same node in AF South 1B. And then we have Orders 2 on AF South 1A, and Products 1 on AF South 1B. Now, because there are lots of moving pieces, it's easy to forget what these different replicas or these different versions represent. So just so we're sure, remember, Orders 1 consists of the list of orders that starts off with Bruce Wayne, and then Steve Rogers, Tony Stark, etc. Whereas Products 2 starts off with the Envoy hoodie, and then Orders 2, James Lake Jr., and Products 1, the Kubernetes t-shirt. So that's an understanding of the deployed topology setup. And this over here is essentially our objective. For this particular demo, I'm going to demonstrate how you can combine Istio's destination rules with the Kubernetes service internal traffic policy. And to control zonal traffic for both load balancer to pod communication as well as interpod communication. And I'm going to send 80% of traffic coming from a load balancer to AF South 1A. So all traffic, regardless of where it's coming from, is going to go to AF South 1A. Now, in a production setup, you don't want to do that. You want to send a majority of the traffic to a certain destination depending on where it's coming from. But in this case, just so we can see that the destination rules are working as expected, that's what I'm going to do. And then I will apply a service internal traffic policy to the product service so that the orders replica is only able to communicate with products on the same node. And the same thing will go for GraphQL as well. So with that being said, I'm going to switch over to the demo. And I'm going to focus on jumping to specific parts. So this is the before, right? So this is what traffic flow looks like before any policies have been put in place. And so the first thing that we're going to look at is the GraphQL request that is being sent here. go. So I'm hitting send, and you can just pay attention right at the bottom over there. You'll notice that there's somewhat of a 50-50 split between the responses that we're getting. You'll see that some lists have James Lake Jr., while the other one has the Bruce Wayne list, and it's a 50-50 split. So you'll notice that over there. Every time I hit send, it's essentially alternating between those two. That is not what we want. Let me get rid of that taskbar real quick. All right. There we go. All right, next up, let's look at the orders request. You'll see something similar over here, basically switching between Bruce Wayne and James Lake Jr. So most of the traffic is being, or rather the traffic is essentially being split 50-50 across the board. Let's take a look at what the map for that looks like. So what we have over here is traffic from the Istio Ingress Gateway. Let's follow the path for a GraphQL request. Goes to the GraphQL service, and then goes to the GraphQL API, and then communicates with the orders service first, and then it speaks to both versions of orders. When that data is resolved, it comes back to the GraphQL API, and the GraphQL API communicates with both versions of products. And if you see the red line over there and you're wondering, well, why is that there? So remember, orders 1 doesn't support the API request for associated products with a particular order. And so that request was failing. But the other one, orders version 2, you'll see successfully goes through the order service to orders 2, which is represented by that image tag over there, 037 alpha, and then manages to successfully communicate with both versions of products. So the next thing I'm going to do is apply the destination rules. We'll jump straight to the results of what that looks like after the destination rules have been applied. So this is now sending 80% of traffic to AF South 1A. Just to refresh your memories, AF South 1A is where there's a list that starts off with James Lake Jr. So you'll notice I'm hitting the send request over and over, and a majority of the responses return James Lake Jr. That's the first appearance of Bruce Wayne, but when I keep clicking it, I'm getting James Lake Jr. responses because 80% of that traffic is being sent there. And this is the same case even if we carry out the tests with the orders API. But now I'm going to jump to implementing the service internal traffic policy. Well, I was not expecting that.
So you get a typo in the time frame.
Right. Okay, here we go. Okay, so this is now going to be live after I've applied the service internal traffic policy. So what's happening is 80% of traffic is going to go to AF South 1A, but because of the service internal traffic policy, that means that requests can only be successful to a product's API if it exists locally on the same node. And so if you recall, the first node in that list that I showed you earlier had a product's replica existing with the GraphQL replica and the orders replica. But that was a specific version of products which starts off with Envoy hoodie. So that means that the only responses we'll be seeing will be the ones that consist of Envoy hoodie. So you'll notice here that at the top over there where it says order 4, that may change. 2 out of 10 times it will be Bruce Wayne, but 8 out of 10 times it's James Lake Jr. Nonetheless, the list of products is not changing at all because all of the traffic is only ever being sent to products 2, which exists on the same node over there. So that essentially brings things full circle of how you can implement both controlling zonal traffic as well as controlling local traffic, or rather localizing traffic to a node to minimize on low latency. Thank you very much.
Awesome, and we have 1 minute to spare for questions, so we'll take this.
Sure.
Thank you so much. I know it's always hard when you have not the mirrored screen, but like the extended screen, then looking like this, and it's really hard to see from here anything. We take 2 minutes for questions. Who has a question? Raise your hand. Everything was crystal clear, maybe? Who knows? Like, how often do you consult people on this?
More of the cost optimization, so the cross-zone traffic, whereas the other one has been a little bit less, but has been coming up more. How do we manage maintaining optimal performance between certain microservices and combining that with cost optimization? Yeah, but it's certainly more of the cost optimization.
Thank you for your presentation. It was really clear, but after applying these changes, now we have pods that are not served. Am I correct?
Yes, that's correct.
Is there any way to scale down those pods because they are not served anyway, automatically?
Yeah, great point. So just remember that the reason I showed the demo in the way that I did was just to show that the policies are actually working. So what you would actually want to make sure of is that you have enough pod replicas across the different topology domains. So that's where pod topology spread constraints comes in handy, so that you make sure that every pod that's deployed in your cluster is actually being made use of, and you don't have situations like that. So that was just for demonstrative purposes to show that the policies actually work. But great question.
All right, one more. One, go once, go twice. Hooray! Break! And thank you so much. Again, a big round of applause for your demo.
Sure.